Welcome back to part 2 of this video. In this video I'm going to talk about parallel twin engines, particularly pertaining to classic motorcycles. In the first video I talked about single cylinder engines. You might want to go back and see that if you haven't already. I will leave a link to that in the comments below this video. So where I left off in the last video, we have a 1-cylinder engine. Now, with some basic balancing added, some weights on the back of the crank, you can smooth this engine out somewhat, but it's still a pretty cantankerous beast. It's still fairly vibey. It only has one power pulse every 2 revs, so it doesn't have a very smooth torque output. So imagine yourself back in the days in the 1800s, when engineers were thinking, what if we had 2 cylinders and 2 pistons operating on this crankshaft? How would you do it? Your first thought might be to do something like this. So your first idea here is to put 2 pistons and conrods on the one crank. And now because you want to put the cylinders side by side, and you have a certain width that you have to work to, and you've got to fit the cylinders in side by side. You can't put these conrods very close together, so you end up with this very long crank pin. So a lot of manufacturers actually did exactly this. There's an example in the photo I'm showing you now of a crank with this arrangement. BSA, Norton and Triumph all had this arrangement, and the Triumphs were produced right through to the 80s. The main bearings, there's only 2 of them. They're very widely spaced. The space between the conrods is taken up by a flywheel cum balancing weight. Other manufacturers thought there had to be a better way to do this, and so this is what they did. So you'd bring the crank back in and put a bearing in the middle here. In other words, what you're doing is grabbing one of these and putting another one side by side next to it. Here's an example of this type of crankshaft. It's from a Laverda 750. It's got 2 bearings between the cranks and a sprocket that drives the camshaft. This is quite a common arrangement these days with parallel twins. So what you've ended up with is 2 pistons going up and down together. You've basically duplicated a single cylinder. Now, in hindsight, that seemed like a dumb idea. You were basically doubling the vibration. If this were a 250cc engine and you made this one a 500 with all the same components, you would be doubling the out of balance forces that are generated, even with the counterweights put on. You've got to remember that back in those days, engines were running very slowly and balancing wasn't really much of a concern, so much as just getting the thing to actually work. So it's only later that they really paid much attention to balancing. Now, the other way of doing this would be going back to the arrangement with a long pin. Rather than having the cylinders side by side, what if you splayed them slightly so that the cylinders weren't restricting how close you could put these conrods together? And what you'd end up with, so because this is in 3 dimensions, you've got to imagine those 2 conrods are actually splayed like that with pistons on each end. If you like, in this view, for example, so you splay the conrods far enough apart so that the cylinders don't get in the way of each other. So the first V-twin was produced in 1889, I believe, by Daimler in Germany. It was a 20-degree V-twin, there was generally no consideration given to balancing in that angle. It was all about just getting these cylinders far enough apart to make the system work. So V-twins have been around a very long time. It only took a couple of years, probably, after the invention of the one cylinder to go on to 2 and more cylinders and in that V configuration. So let's park V-twins for the moment and go back to parallel twins. The 360-degree parallel twin, as it's known, has both pistons going up and down together. Now that's not a great thing as far as balancing goes, but it does have some advantages, one of which is the even firing pulse. Okay, each cylinder fires once every 2 revolutions, but because there's 2 of them, it'll be one cylinder firing every revolution. This one will fire on 1 revolution, and this one will fire on the following revolution. Another advantage is you can have a single ignition system in what's called a wasted spark situation, so that both cylinders actually fire every time the piston comes up to opposite dead center. The one that's not on the one that would be on the exhaust stroke or coming into the intake stroke will fire as well, but nothing will happen because there's no charge there. So it's just a little bit simpler for as far as ignition goes. One disadvantage is you get a lot of pumping, what's called pumping losses, because these pistons are going up and down together. The volume inside the crankcase is greatly increasing and then decreasing. So you've got to pump air. It acts as a big pump, essentially pulling in air and then pushing out air through your crankcase breather. So you get a bit of power loss there, and you have to deal with a lot of air moving through the crankcase, which can be problematic. Now, this might be a good time to point out that I haven't talked about balancing shafts or other methods of balancing these engines. Up until probably the mid-70s and even early 80s, there were very few motorcycles that had any kind of extra balancing shafts. With well-designed balancing shafts, you can pretty much make almost any engine smooth with enough complexity. There's been some very ingenious ways of balancing this inline 360-degree twin. BMW, for example, on their F800 more modern engines, actually had a very thin crank coming down here between the 2 cylinders. It had a very short, in effect, conrod here and a big link, pivoted link, which had a weight on it. So it in fact acted like another cylinder on this end, but obviously sized to compensate for the out of balance forces of 2 of these cylinders. So every time the cylinders go up that way, that conrod would move down, and when they came back, it would come back. I'll show a picture of that now, just as an example of what clever ways people have come up with for balancing these things. Some other advantages of this engine, it's usually mounted across the frame, as in the crankshaft is across the frame. It gets pretty well cooled. It does, like all inline engines, you're not getting a lot of cooling between the cylinders. So if the cylinders in plan view sit like that, and you've got your fins generally around like that, and the breeze coming through this way, they get fairly well cool, evenly cooled, not so well through the middle here, and not so well at the back, but not too bad. It's a lot better than a narrow angle V-twin, inline V-twin, for example. They're quite compact, cheap in that you can have one, in effect, cylinder block, and you can have one head, and you can drive all your valves through one drive system rather than more than one, as you would on a V-twin or a boxer or other arrangement. Some examples of motorcycles using the 360-degree parallel twin engine. The Triumph Bonneville, it was one of the models that really set the parallel twin as an icon of motorcycling. There was also a more recent retro version of this. There was the Norton Commandos, the Laverda 750, the Kawasaki W Series 1, 2 and 3. It also had a more recent retro version known as the W650 and 800. The XS650 Yamaha. This was very much influenced by the Triumph Bonnevilles. The TX750 Yamaha. This bike featured twin counter-rotating balancing shafts, which made it quite a smooth machine. Okay, for parallel twins, there's a couple of other arrangements of the crankshaft we need to talk about. The first one is the 180-degree parallel twin. It would seem to make more sense if you're going to have two cylinders to actually try and use the motion of the pistons to improve the balance. So what you do is, rather than have what is in effect one crank, you move this crank 180 degrees so that the pistons actually alternate their motion and completely oppose each other in their motion. So that would look like this. So while one piston is at top dead center, the other piston is at bottom dead center, and vice versa. So in this axis or direction, you've got perfect balance. The forces in one piston always are opposing the forces in the other piston. Now, as with most things, there's always a downside. So while it is perfectly balanced in this direction, what you end up with is what's called a rocking couple or moment. Because these aren't in alignment, when this piston comes up to top dead center as shown like that, there's a force there in that axis, and this one is causing a force this way at that axis. So you've got a separation of these forces by that much, and that gives you this rocking couple. And when the pistons move to the other position, the forces go in the other direction. So side to side on the crankshaft, you've got this vibration that wants to rock the engine. These rocking forces are less of an issue than the reciprocating forces generated by the pistons in a 360-degree crank engine. The forces are usually left unchecked in smaller motorcycles up to 500cc. In more modern engines, these forces can be removed using a balance shaft. Another advantage of this design is that there's virtually no pumping losses at all. As one piston rises to increase the crankcase volume, the other descends exactly the same amount, thereby leaving the crankcase volume always constant. This also makes managing crankcase breathing a lot easier. It's probably worth at this stage taking a bit of time to talk about secondary balancing forces. These forces are known as secondary imbalance forces because they occur 2 times per revolution, whereas primary imbalance forces only occur once per revolution of the crank. I won't go into it in great detail here, but suffice to say that the forces are caused by the different acceleration rates of the pistons in the top half of the stroke to the bottom half of the stroke. If you do the geometry, it's pretty easy to see that in the top 180 degrees of the crank revolution, the piston actually moves a greater distance than in the bottom 180 degrees of the crank. And thereby that means that the piston has to accelerate faster in the top half of the stroke than the bottom half. This causes higher frequency vibrations in the engine, and they are compounded when the pistons move, when you've got more than one piston moving together. So that in the 360 arrangement, where both pistons go up and down together, you do have a lot of secondary vibration. This one, however, because the pistons are not moving together, you don't have as much of an issue with secondary vibrations. They're still there, but less so. Secondary unbalanced forces are more pronounced at high revs. It's also very common in four-cylinder engines because you actually got two pairs of pistons moving together. So while a four-cylinder is perfectly balanced in primary forces, it's fairly bad in secondary forces. So getting back to other disadvantages of this arrangement, first of all, the firing is much more uneven than a 360 degree parallel twin. Because of this arrangement, you will have one cylinder firing, and then 180 degrees. This one will come to the top and fire, and then you will have 3 times 180, which is 540 degrees of motion of the crank and before the next one fires. It's really as uneven a spacing as you can get for a two-cylinder. Now this gives it a sort of lumpy feel and a lumpy sound. Some people love the sound. Some people say it gives it a lot of character. So some examples of motorcycles that use this 180 degree arrangement: there was the Honda CB 350 and 450, the Laverda 500, it actually had a balance shaft in it. The Yamaha TX 500, it also had a balance shaft. There was also the Ducati 500. They made a parallel twin for a short amount of time. It was a pretty little thing, but very unreliable. And the other arrangement of the crank to talk about for parallel twins is the 270 degree crank. Now this is something that's only really a more recent development in more modern engines. Rather than 180 degrees between the cranks, you swing one of these cranks over 90 degrees. So you have the two cranks 90 degrees apart or 270 degrees apart in the other direction. This is kind of a compromise between the 180 degree crank and the 360 degree crank. A lot of the reason it's done is to give it a bit of a lumpy feel to it. And it's very much a copy of a 90 degree V-twin. They sound very much like a 90 degree V-twin, and they have that feel too. They make a very nice sound. The thing with a 270 degree crank is that you need to use balance shafts to make it the balancing reasonable. That's why it's more of a modern engine design. Compared to the 180 degree crank, you are not getting as good a balance in this direction. That's why they make use of a balancing shaft to improve that. And also the rocking couple is actually better or less vibration due to that rocking couple, because the pistons are not exactly out of sync. One is sort of mid-stroke while the other one's at top dead center, and they kind of follow each other slightly out of sync. So the rocking couple is a lot less. They have worse pumping than a 180 degree crank, but much better than a 360 degree crank. The firing pulses, as I said, are more uneven. So what you have is 270 degrees between the first pulse and the second pulse, and then you have, 450. That's right, isn't it? 720, yep. So 270 between the first pulse and the second pulse, and then 450 back to the next pulse. In regard to secondary forces, again, the pistons aren't moving together, so it has a similarly low secondary unbalance compared to the 180 degree crank, but it's much better than the 360 degree crank. Some examples of motorcycles that use the 270 degree parallel twin. The first, I believe, was the Yamaha TDM and TRX 850s in the early 90s. Yamaha seems to love this engine. They used this type of engine in the Yamaha Tenere 1200 and also in the MT-07. Honda uses it in their Africa Twin. There's the new Triumph Thruxton 1200, as distinct from the earlier versions, which were a 360 degree crank. And there's the KTM 790. This is actually a 285 degree crank, and the reason it's done like that is they're trying to mimic the 75 degree V-twin that they use on their Super Adventure 1290 and the RC8. Now let me try and demonstrate how each of the different angles work on the cranks for these parallel twins. You've got a 360, 180 and 270. With the 360 degree crank, both crank pins, if you will remember, are in the same axis, so both at the top. So bang, one cylinder will fire, it'll rotate 360 degrees, the other cylinder will fire, bang, etc. So bang, bang, bang. As you can see, it's a very even power pulse distribution, torque output, if you like. The 180 degree crank has one crank pin at the top, one at the bottom, or 180 degrees apart. So first cylinder fires, bang, 180 degrees later, the next one will fire, bang. Then you've got to do 1.5 turns, or 540 degrees, until the next one fires again, bang, 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 bang. As you can see, it's a very uneven firing pulse. For the 270 degree crank, you've got one crank pin at the top, the other one 90 degrees apart, or 270 degrees in this direction. First cylinder fires, bang, 270 degrees later, next one fires, bang. Then 450 degrees later, 1.25 turns to the next fire, bang, 270 degrees, bang, 450, bang, 270, bang, etc. As you may have noticed from the photos I've shown you during this video, almost all motorcycles with parallel twin engines have them mounted transversely or with a crankshaft running across the frame. The cylinders are generally vertical or inclined forward somewhat. The only exception I've seen to this is an early Sunbeam. It was a inline parallel twin, that is with one cylinder behind the other. It would not have been a good arrangement for cooling of that rear cylinder. It was shaft drive, which made sense as the crankshaft was running longitudinally in the motorcycle. So that concludes this video. The next video will be about boxer twins or flat twins. Thanks for watching.